Welcome back to the Explainer. Okay, let's dive into this. A drill ship's thruster, it isn't just a basic motor and a propeller hanging off the back of a boat. No way. We're talking about a highly complex, sealed, permanently submerged machine operating in literally one of the most unforgiving environments on the planet. Today, we're looking at the hidden life support systems of these thrusters. We're going to uncover exactly how engineers keep these massive units functioning under intense pressure and heavy loads hour after hour, absolutely without fail.
5.5 megawatts. Just let that number sink in for a second. That is the massive, continuous electrical load running through just one single thruster pod on a vessel like the GF 12000. To put that into perspective, that's enough power to run a small town. Now, when you submerge a machine generating that much power deep under the hull, well, it basically becomes a ticking time bomb without active thermal and pressure management. If its support systems fail silently, the thruster itself is the very next thing to go. It'll overheat, seize up, or flood internally within hours.
So to prevent that kind of catastrophe, the engineering design relies on a rule of three challenge to keep the thruster alive. We've got hydraulic steering, cooling water loops, and seal oil gravity tanks. Let's look at each one.
First up, hydraulic steering.
Now think about it. When you don't have anchors holding you to the seabed, how do you physically direct this massive amount of thrust to keep the ship perfectly on station? Well, in plain language, you can think of the thruster's hydraulic steering system a lot like the power steering in your car, right? The power steering physically turns your front wheels. But look at the scale difference here. The thruster's hydraulic steering isn't just turning a small wheel. It's rotating an entire 5.5 megawatt pod, and it's doing it through a full 360 degrees. This independent hydraulic steering gives each individual thruster the ability to reach its commanded azimuth angle instantly. It means the thruster can push in absolutely any direction to counteract wind, waves, and current without the whole ship having to turn like a traditional boat would.
Moving on to challenge number 2, cooling water loops.
Okay, so once you have the thruster pointing the right way, you have to deal with the immense heat being generated by that submerged motor and gearbox. To beat that heat, the system relies on independent cooling water loops. It acts very much like a car radiator, passing cooling fluid through a heat exchanger to strip away the heat generated by all those moving mechanics. But pay close attention here. This is a dedicated, per-thruster system designed specifically to prevent cascade failures. They definitely do not use one giant, shared cooling system for all 6 thrusters.
So, the crucial point is, one loop equals one thruster. This is a very strict, deliberate redundancy choice by the naval architects. If one cooling loop fails, clogs, or springs a leak, it should only ever take down that single corresponding thruster. By keeping the water loops physically isolated from one another, a minor fault in one subsystem can never wipe out multiple thrusters and compromise the whole ship's ability to hold its position over the well. It's a real game changer for reliability.
And that brings us to number 3, seal oil gravity tanks.
Think about the physics here for a minute. You've got a permanently submerged gearbox and a rotating shaft poking right out of the housing into the ocean. How on earth do you guarantee seawater doesn't force its way inside? Well, I love this quote because it perfectly captures the brilliance of the engineering. The system actively outpressures the sea, so oil always wants to leak out rather than water leaking in. The seal doesn't just sit there as a static, solid barrier just hoping the water doesn't push past. It actively pushes back. You can think of it exactly like a scuba regulator. It's constantly balancing the pressures so that whatever's inside the machine is staying at a higher pressure than the water outside, all without needing a human or an active pump to react in real time. It's just a completely brilliant passive failsafe.
To achieve that failsafe, we use this core engineering definition. The required seal oil head pressure must be strictly greater than the external seawater pressure at the depth of the seal. The system uses an elevated gravity tank, which is essentially an expansion tank mounted high up inside the ship's hull. By using the natural weight and gravity of the oil sitting way up high above the thruster, it guarantees the internal oil pressure beats the external ocean pressure. Because it relies purely on gravity, it never needs an active pump to maintain that pressure barrier. Plus, it safely absorbs any thermal expansion of the oil without letting pesky air bubbles into the seal path.
And this brilliantly illustrates how everything we've learned ties together. Remember our earlier explainer on operating drafts? When a drill ship balls down from its transit draft to its 11-meter drilling draft, it sits much deeper in the water. At that depth, the external sea pressure pushing inward against the thruster seals easily exceeds 2 bar.
Therefore, the gravity tank has to be elevated high enough inside the hull to guarantee the outward-pushing oil pressure comfortably beats that 2+ bar at all times, no matter how deep the ship drafts.
Which leads us to our final section, early warnings.
Understanding the theory is great, but we really need to shift our perspective to real-world operations here. How do operators actually know if these lifelines are healthy? Let's test your new intuition about these pressure systems with a practical scenario. Imagine you were doing your rounds, and you notice that the seal oil level in the gravity tank's sight glass is slowly dropping over a period of several days. There are no other alarms going off. What do you suspect is happening? And critically, what should you do about it?
Well, the absolute most important rule is do not just top it up and ignore it. Now, the oil leaking out actually proves that the passive system is working exactly as designed, right? The gravity tank is successfully outpressuring the sea, pushing oil out, rather than letting seawater in. However, that slowly dropping sight glass is a massive early warning. It tells you there is a developing seal leak path or worsening seal wear. If you ignore the root cause and just keep adding oil, well, that minor wear will eventually escalate. You'll lose your pressure margin entirely, and that simple worn seal will turn into a fully flooded, catastrophic failure of the thruster housing, and nobody wants that.
And with that, your understanding of the entire thruster package is complete. You now know how they generate incredible thrust, how they safely retract into the hull, and how these vital auxiliary systems, the steering, the cooling, and the seal oil, keep them alive and functioning under really extreme conditions. But it leaves us with one massive, provocative question. How do you perfectly command and coordinate 33 megawatts of power across 6 independent units, battling storms and currents in real time, just to keep a massive ship locked within meters of a target? Next time, we're going to dive into the DP3 brain, the dynamic positioning system that makes all of this engineering magic possible. You won't want to miss it.